Okay. So, good morning, everybody. This is the YouTube live stream link, and I'm sharing it on Telegram also. I'm starting the recording on my computer also. Okay. Good morning, everybody. Those of you who thought there was a quiz today, I'm sorry to disappoint you. The quiz will be held probably tomorrow or sometime later this week. But the main thing is that it can come at any time. So please attend class. If you are not present during the quiz, then that will be your loss. Okay, so let's see. So 40th online class. Okay, now somebody had something to say. Okay, Vipul, tomorrow is another quiz. So if I have my quiz on tomorrow, then you will just have 2 quizzes on the same day. Okay. But if you have studied and done the preparation, then it's not going to make any difference for you. Okay. So, all right. So we were talking about coherent states, and I had explained how coherent states are supposed to be states which saturate the Heisenberg bound, which means they are states with minimum uncertainty. And we will see that these states correspond to, can be expressed as eigenstates of the destruction or annihilation operator, right? So these are obviously not number operator eigenstates, because number operator eigenstates are not eigenstates of the annihilation operator, right? So then what are the properties of coherent states? Well, one property, for instance, is that if you take the expectation value of the Hamiltonian, the energy of the state, that comes out to be equal to amplitude of alpha squared. Then, and of course, plus a factor of alpha half. And then there is this completeness relation, which I'm sure you know. That completeness relation we can do some manipulations to show that there is a recursion relation relating the Cn, this is Cn, and then this quantity becomes Cn minus 1. That is the coefficient of alpha when alpha is written as a sum over the eigenstates, the number operator eigenstates. This you can iterate this recursion relation to find out that n of this inner product of n alpha, which is equal to C of n. So right, where did I write down an expression for C of n? Let me just put that here. Alpha is equal to summation over n, C of n alpha. Okay. Is there some lag in my okay, so this is C of n, and then this quantity becomes alpha n root of n factorial C0. So C of n can be expressed, all the coefficients can be expressed in terms of C0. So once we know this, we can write down the full expression for alpha. Now, to proceed further, we need to define something called a displacement operator. But before talking about the displacement operator, which is needed for the case of coherent states, we will first I will discuss a few identities, a few operator identities which will be necessary as we go forward. Okay. So what are these identities? So the first identity goes like this. Let's say that you have let's say that you have two operators, A and B. These are operators. And by the way, there is a certain notation for operators. So for instance, when we have a state, we write it like this. We say that this state belongs to the Hilbert space, right? What is an operator, right? An operator is something which takes the Hilbert space to itself, right? Because an operator acts on a vector and gives us another vector in the same Hilbert space. So we can also write an operator like this, right? So we can say A comma B, A comma B, they are operators. And so we have the following identity. If I take this product, so this is the product that we are going to be looking at. This can be written as a sum. So this is like a Taylor series. Okay, so this is sort of like a Taylor series. You can imagine that this quantity, you can think of it as a function of B. B is an operator, but I'm saying that, well, taking B as an argument, right? You can have functions of operators also. Exponent, for example, is a function of an operator, right? So if you expand this operator, the first term is just the operator. The second term is alpha times this commutator. The third term is alpha squared by 2 factorial. And this is a nested commutator. So we take the commutator of AB, then we take the commutator of A with that whole thing. And then in this way, for example, the term after this will be the commutator of A with this whole expression. So that means whatever came in the last expression, we take the commutator with that, like that. Okay, so the first thing we will do is we will prove this identity. Okay, now, well, actually, I'll leave the proof. I don't know if working out the proof in class will necessarily be enlightening. So I'll prove this one identity. Then there is another identity. It's that proof I will not give you. Okay. So first of all, let's write this expression as a function. Okay, but before giving the proof, let me explain to you what is going on here. Okay. So what is the general idea? What are we trying to do? see what happens is that now remember that when you have a unitary operator, okay, U, let's say, then one of the things that we have seen is that transformations of the Hilbert space, right, which preserve probability. That means to go from one state to another state such that the norm of the state is preserved, right? This requires the action of operators which have this property, unitarity. So you can call it unitary, you can call it unitarity, right? So these are like coordinate transformations. Just like in classical mechanics, we have coordinate transformations, right? Similarly, here, what are the coordinates of our system? The coordinates of a system are given by the state vectors. So if you're changing the state vectors, this is like performing a coordinate transformation. Right now, under this transformation, what happens? The vectors transform in this way, right? But let's say I have some operator relationship, like some operator acting on the state psi. Then how should this transform? Right? Will it be equal to, for instance, A times psi prime? Right? It's not going to be equal to A times psi prime, right? Because in order for the relationship to be consistent, whatever identities or relationships there might be, A also has to transform, right? So how should this whole thing transform? This should transform as U times A psi, right? So because this is a state, A psi is also a state. So the action of U on all states is of this form, right? So U should act on this state to give me A psi. Now this expression I can write like this: U times A, and now I insert a copy of the identity, right? So if I insert a copy of the identity, that means this is U inverse times U. That's just the identity operator, right? Times psi. Now you see that there are two parts. This is psi prime, right? This is a transformed state. And then what is this guy? This guy is a transformed operator, right? So under the action of this unitary operator, what happens? States transform like this, and operators, they transform like this. Okay. So now if you look at this expression sort of looks like the previous expression, right? It's not, I mean, it's not exactly the same, but it looks like it. So if you say that the unitary operator U is, let's say, exponent alpha A, okay? And you say that U inverse is exponent minus alpha A, right? And you can see that this is true, right? Because if you take exponent alpha A, multiply by exponent minus alpha A, you get the identity, right? So this statement, this expression is exactly like taking a unitary operator and transforming, acting on all operators, whatever operators there may be. Right? This is a similarity. This is called a similarity transformation. Okay. So in classical mechanics, we often use coordinate transformations to simplify the form of our Hamiltonian, for instance, or the Lagrangian. So when we have a problem that is difficult to solve in one set of coordinates, we transform to a different set of coordinates, and such that the problem becomes easier to solve in those new coordinates. So this is basically in the same spirit, right? We are transforming to a new set of states. So this is a similarity transformation. F1 alpha is e to the alpha a b. Maybe a little bit more careful. And we can write this as u times b, u inverse. Also, instead of writing e to the I alpha, you can also write it as this exponent alpha. Okay. It just depends on whatever you find convenient. Now, what's the next thing? So initially I said that, well, this is like a Taylor expansion. We are talking about this identity. And I said this identity is like a Taylor expansion, right? So we have defined this function f of alpha and f1 of alpha. So, well, let's perform a Taylor expansion of this quantity in terms of alpha, right? So if I have this function f1 alpha, if I want to write down the Taylor expansion around alpha is equal to 0, how will I do that? First term will be this. The second term will be alpha times f1 at 0. So the prime denotes the first derivative, right? Then at 0, and then so on, right? This would be the Taylor series expansion of any function around 0. So let us evaluate these different terms. Okay, let us look at, we have this expression. Let us evaluate these different terms. What is f10 first of all? So f10, I just put alpha is equal to 0. This becomes the identity, this becomes the identity, and this just becomes the operator b. Okay, now let me calculate the first derivative of alpha, right? So now I'm going to calculate the derivative of this quantity with respect to alpha. So how do I do that? Now, so we have the Leibniz rule, right? What does the Leibniz rule tell us? That if you have something like this, right? You have a product. So here, what do we have? We have a product of 3 terms. And we have to be careful about maintaining the order of the terms because A and B don't commute with each other, okay? So if you take this derivative e to the alpha a b to the minus alpha a, right? You take, so basically it will just be, instead of 2 terms, you have, instead of 2 factors, you have 3 factors. So you will get 3 terms instead of 2 terms. So the derivative of the first term will be alpha e to the alpha a. So this will be, okay, let me write down slowly. D e to the alpha a, d alpha BE plus alpha A plus E to the alpha A. Okay. And well, this quantity is 0 because B doesn't depend on alpha. Okay, so you get two terms like this. Okay, now what is this derivative? Well, this derivative will just give you this expression. Okay, and now note that A is an operator, right? But if you take an operator and you take the exponential of that operator, both of those operators, they commute with each other. So that means you can write this quantity in this way also, because E and E to the AA is 0. Okay, this is something you should convince yourself of. You can write E to the A as a series expansion, right? And each term of the series will contain either the identity or some function of A. So any function of A will commute with A, right? This is true in general. So this is something that is useful to remember. Any function of A will commute with A. Okay. So what happens now? D alpha, F1 alpha. The first term gives me this A times E to the alpha A, and I'll put the A on the inside. It doesn't matter where, I can put it anywhere I like. I'll put it on the inside. And the rest of the term is B times E to the minus. So the reason I'm doing this derivation is because I want to show you how to deal with these operators, operator products, and derivations of these functions of operators. Because if you're not careful when doing this, you will make many mistakes. The second term, this term, when you take the derivative, instead of, you will get minus A, right? And now where will that A go? That A will come after B. So the second term will become E to the alpha A. I'll bring the minus sign outside. B times A E to the minus alpha, like this. So now what is this? This whole thing I can write as E to the alpha A times AB minus BA E to the minus alpha, right? Because this is multiplied on the left by this same factor and on the right by the same factor. And this can be written as E to the alpha A, commutator of AB, okay? So you have to go through this calculation on your own also and convince yourself that you understand what is going on here, okay? And so now we can write down F1 prime at alpha is equal to 0. So this is the first derivative. When you said alpha is equal to 0, what do you get? You get AB. Okay. Now what about the second derivative? Well, now the second derivative, you can see what the pattern is. When you take the second derivative, again, exactly the same procedure you can follow for the second derivative. You'll get a derivative of this term and a derivative of this term, and this term will not give you anything. So what will happen? You'll get E to the alpha A, and then the derivative of this will give you A, and then times AB, and the second term will give you AB times A, and then minus alpha, right? Exactly the same thing will happen, right? And this can be written again as e to the alpha a. And now what is this? This is the commutator of a with ab, right? So you can see this pattern emerges, right? This pattern of nested commutators, it emerges naturally when you take this derivative. So f1 double prime at alpha is equal to 0 is this commutator. And the same thing will be true for all the higher terms, right? So what will happen? So if we expand this in powers of alpha, what will we get? The first term will be f of 0, right? F of 0 will just give me b. The second term will be alpha times f prime 0, right? So I should clarify that I'm writing that this is a function of alpha, not a function of b, right? So you can see how this series expansion comes about. These are just the different terms in the Taylor expansion. These are the coefficients, right? So then this gives us, right? These are just the various terms. This is B. This is a commutator AB. This is commutator of A with commutator AB and so on. And so then this implies that this F1 alpha to the alpha AB minus alpha is equal to B. What is the first term? AB. What is the second term? Commutator of A with AB. What is the third term? Commutator of A with what? Commutator of A with all of this, like this, and so on. Okay, so this is our identity that we wanted to prove. Okay, and so this identity is very important. It becomes the foundation of something known as something called the BCH identity, which stands for Baker, Campbell, Hausdorff. Is there one F or two Fs? One F identity. So this is not the BCH identity, but this identity becomes the foundation of the BCH identity. Now, before doing that, let us consider a special case. So let us consider a case. Let the commutator of A and B be equal to C, where C is just some complex number. Okay. Now it's kind of obvious where we are going with this if you think about it. What are examples of some operators whose commutator is just a complex number? We have seen those operators before. Right? These pairs of operators, their commutator is just a complex number, right? So first of all, let us say that this is the case. And also, so if this is the case, right, then this will imply that what will this quantity be now?
Zero.
Zero, right? And so will all the higher terms, right? So what will happen with this expansion? E to the alpha a b, e to the minus alpha a. The first term is b. The second term is alpha times ab, and then all the other terms are 0. Right? So what do we get finally? What is this? This is a constant C. So finally, we are left with this expression. This transformation is equal to the operator B displaced by this amount. And it's understood that you should put an identity here. So right. So when we say that the commutator of two operators is a number, it's understood that it's a number times some identity matrix, right? Because if these are matrices, then you should also have a matrix on the right side. And so this, what is it doing? It's causing a displacement, right? It's causing a displacement of B by some amount. As a simple example of this, we can consider this kind of a situation where we take B to be X and A to be the momentum operator, right? Now, what is A commutator B? A commutator B is equal to IH bar. So what is this quantity become? This becomes X plus alpha times C. And what is C? C is alpha is IH bar, right? So this is displacing X by this amount, right? Now, so if I write alpha is equal to minus I, and then let's say delta X by H bar, right? Then what will this be? This will be X hat plus delta X, right? What is this? This is a translation. You can put an operator on this X, though when this acts on position eigenstates, you will just get a number. So this is a translation or a displacement. So what is meant by displacing X? And displacing X just means that you are performing a translation of your state by this amount, right? You're just moving. If you have a particle at a point X and you act on that particle with this, what will you do? So as I explained earlier, these unitary operators, they act on states in this way, right? On operators in this way, right? But they also act on states in this way. So corresponding to the action of this is our operator. How does this operator act on a state? Now we can ask, how does this operator act on a state? We have seen that it acts on the X operator by moving it by some amount. So let us ask, how should it act on a position eigenstate? Okay. And if I can write down the action of this on a position eigenstate, then I can write down the action for any arbitrary state, right? Because these are the basis states. Okay. So what will this be? This will be equal to x plus alpha. Right? So what does it do? It takes the position eigenstate and so alpha c, sorry, where c is this commutator. So again, so that's why this quantity is called the translation operator. So if you write this as e to the minus I delta x by h bar times t, this is called the translation operator, right? And this is another reason why we refer to the momentum operator as the generator of translations. Okay. So I'll pause here for any questions. There must definitely be questions that people have. But again, see, all of this you have to sit down and work through on your own. So I'm going to so I'll send you some homework problems related to this. Okay. But basically working through all of this is a homework problem in itself. Okay. Right. So what is the purpose of doing all this? You remember that now we can come back to our notion of a displacement operator. Remember that we defined this operator in this way, right? If you go back to the previous class, the displacement operator, we defined it as the operator which takes the zero state and creates this alpha state. Well, what is alpha? Alpha is the eigenstate of A, right? Now, this you can see can be written as 0 plus alpha. Okay. So alpha is obtained by displacing 0 using d alpha, right? So from the previous discussion, all of this discussion, right? We know that this d alpha, it will be of the form, it will be of this form, right? So it will be unitary. Okay. So see, I have not defined the displacement operator yet, right? So, but I know that if it's of this form, it will be a unitary operator. If this A is Hermitian, by the way. So if you take the exponential of a Hermitian operator, you get a unitary operator, right? Then what is the inverse of this operator? E of alpha A inverse is e to the minus alpha A. What is this? This is d to the minus alpha. And what is this? This is equal to D alpha inverse. Right? So we immediately get these properties of this D. What are the properties of this D alpha? Okay. Number one, it is unitary. D okay, D minus alpha. Number two, okay, all right. So if you look at the notes which I shared with you on Telegram, right, on coherent state, in those notes, the author starts off by defining D alpha as some product of exponentials. So I have not done that yet, right? I started out by first motivating what the term displacement operator means. Why should we call it the displacement operator? Right. So now we come to this property, which is the displacement property. This is the displacement property. Okay. So if you perform this similarity transformation on the annihilation operator, you get the annihilation operator is displaced by an amount alpha. Number three, the third property. So it displaces the annihilation operator by alpha. What does it do to A dagger? It displaces A dagger by an amount given by alpha complex conjugate. Right? Alpha is a complex number in general, right? And finally, we have a fourth property, which relates this, the product of two of these D alphas and D betas, and then, so if you take D alpha times D beta, that can be written as D alpha plus beta times something. This we'll talk about later. Okay, I don't want to mention it now, it will just confuse you. So these are the properties of this displacement operator. And you might think that, well, this is a lot of, work. What are we trying to do? What we are trying to do now, if you remember, we going back to our definition of what a coherent state is. A coherent state is a eigenstate of the annihilation operator. And then we used this completeness relationship to write down a recursion relationship for the coefficients of this state. Right. So this is a recursion relationship for the coefficients of right. What is this? This is the statement that C of n is equal to alpha by root n, C n minus 1. This gives me a recursion relationship. Then I apply this recursion relationship to write down the coherent state alpha in terms of my number operator eigenstates. But this factor, what is this factor? This is C naught, right? The recursion will Cn minus 1, Cn will become in terms of Cn minus 1, which will become in terms of Cn minus 2. But all of that series will terminate at C0, C naught. So we don't know what this C naught is, right? We're trying to figure out what this C naught is. So for that purpose, that is where this displacement operator will turn out to be useful. And then we have to understand what are all these properties of displacement operators. Okay. And that leads us to this point. All right. So I'll stop here for the time being. Are there any questions?
So I have a doubt.
Yeah.
So you wrote a relation e raised to alpha a b raised to minus alpha a is equal to b plus alpha c, right? So we substituted as a is equal to p and b is equal to h operator. Then we write as it's h plus alpha I h cut, right? Sir, but c is equal to commutator ab.
You have to remember.
Yeah, commutator ab. That means, yeah, that means commutator ph,
right.
no?
So that is the commutator of
ph.
xp.
No, sir.
px. Sorry.
Yeah, ph.
ab.
Yeah.
Sorry. So c is commutator px. So
yeah.
So there'll be a minus sign, right? That's what you're saying.
Yeah. Yes, sir.
Okay, good. That means you were actually listening to the lecture. Fine. Is that fine? So it's a change of sign. So this will give us this answer now, right? Okay.
Yes, sir.
Okay. Any other questions? Okay. Now what's my plan going forwards? Let me give you some idea. Okay. So what are all the topics that we have covered so far? We covered basically the postulates of quantum mechanics, right? Measurement, composite systems, and we will talk more about composite systems later on. Okay. Right. Then we introduce the Schrodinger equation. Right. And then 1D infinite potential well. Harmonic oscillator. So these are the topics we have covered so far, right? And we have started with coherent states. So it seems like a lot of work in a short amount of time. But don't worry too much, because later on I will we will slow down the pace at some point. Okay. So what's next, right? What do I plan on working on next? Okay. So the topics coming in the future: finite potential well, right? So all of this, not coherent states, all of this you can consider as the contents of my PH703 for minor students, for those taking the physics minor, right, the BTech students. Then all of this onwards is PH703 for MSc. Okay, so finite potential well. Then we will talk about this thing. This is in 1D. Then we will talk about this potential well, infinite potential well only, in higher dimensions, in 2D and 3D. Okay, this is relatively straightforward, but it allows us to introduce very important ideas which you will use throughout your MSc. For instance, density of states, right? Then what else? Some and other topics, not necessarily in this order, will be perturbation theory, right? There are two kinds. One is time dependent and time independent. Okay. Then potential well in 2D and 3D, and also there is something called a spherical potential well. So we'll talk about that also. Then perturbation theory. Then we have to talk about the most, prototypical example of a quantum mechanical system, which is the hydrogen atom, right? So we will be talking about the Schrodinger equation in spherical coordinates. So this will involve bringing all of your definitions of the gradient, this Laplacian in spherical coordinates, and the decomposition of the Laplacian. So you will get things like Bessel functions and hyper and Laguerre polynomials and all of those nice things, which you hopefully will cover in mathematical physics. All right. And then we'll see how much time and interest and enthusiasm there is left to talk about some other topics. But yeah, this is the plan moving forwards. Okay. And then your breakup of marks and all that. You'll be up 60% of the weight. Okay. And then you will have 2 quizzes. Actually, let's make that a little less. Let's make that 40%. 2 quizzes which are worth 20%. 1 mid-sem, which is worth about 20%, and 1 end-sem, which is worth 20%. Okay. So far in homeworks, you have submitted, I think, 4 homework sets so far, right? And the 5th homework set I've given to you. I haven't set a deadline.
Sir, not the 4th one yet. The deadline
Not
is
the 4th
tomorrow.
one. Oh, okay, tomorrow, right? Right. Then after this, well, you would probably have about at least a total of 8 homework sets total. This is at least. Okay. So this is your course plan. I hope everybody is happy with this course plan. The textbooks, well, there are very lots of textbooks you can use. You can use textbooks by there is a really good textbook by Zetley. Other than that, there's a textbook by Griffiths. But ultimately, there is only really one textbook, which is Google. Right? And that's how pretty much I construct all my lessons. So I decide what I'm going to talk about, and then I go to Google and put that into Google, and I use whatever references it's shown up. So as I find those references, I also share them with you, right? So, okay. Any questions? Right. Well, I hope that this satisfies your request for a course plan. Okay. All right. So I'm going to